as we're getting into physics in Calc 1, it's really important to do these in order, so I normally don't do this, but make sure that you watch number 1 and 2 ahead of time here, because it's going to become progressively more difficult. Okay, now in this problem it says a stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60. Doesn't matter the unit for us. Find the rate at which the area within the circle is increasing after 1, 3, and 5 seconds, and what can we learn from this? Well, it might not surprise you, since we've been learning derivatives all semester, that we're going to be using a derivative to do this, right? And one thing we want to remember is that acceleration creates velocity, and velocity creates distance. So what have they given us here? They gave us a speed of 60 centimeters per second. So we pull that out of the word problem and we say velocity equals 60. And what does that mean? Well, they are asking us about areas and the rate of that area change. That's not a velocity. Area is something more like in the distance category, isn't it? Because it's traveling a distance. They want to find out the rate at which it's increasing. So we're going to rewrite velocity. It's not really a velocity in a way, because it's kind of, it's starting as a circle and it ripples outward. They're saying the ripple's moving out at a velocity of 60. But the area itself is this whole space here. And as that increases, maybe it's different with each second. Look at the size of this ring. That might be even bigger each time. So let's see what happens here. The first thing we want to do is understand that velocity is a rate that creates distance, which means we're going to change the name of this to dr dt. And that's going to be the notation for the change in radius versus the change in time. And that's what it's doing, a circular ripple outward at a certain speed. So d meaning delta meaning change, dr dt, like that, is equal to 60. That's very important because we can compare that. Now, area is what we're going to play with, right? They want to know how the area is changing, so they want to want the derivative of area. Then the area of a circle is pi r squared. I think we know that from geometry. So what do you think we might get if we want to take the derivative, which they'll call dA dt? And that means the change in area over time. How fast is the area changing? Well, we take the derivative. That's going to be 2 pi r, and then chain rule, because this r thing is a changing thing, isn't it? That's what this is a function of, so it's dr dt. And we know what that is. That's 60, right? They told us that. So we're going to say the change in area is equal to 120 pi r. I hope you're with me so far. And then for r, well, that's just dependent on time, isn't it? Because we know what the radius is. The radius is equal to 60 times however many seconds it's been. So after 1 second, it's going to be 60. I'll write it over here just to keep it. After 3 seconds, it's 180. And after 5 seconds, it's going to be 300. So all I have to do is plug these in here like this for r, and you get my different values. And when I multiply with pi, I did it ahead of time just so it doesn't get wild. The first answer for 60 after 1 second is like 22,619 centimeters squared per second. And after 3 seconds is like 67,858 centimeters squared per second. Notice that's square is an area per second. It's the change in area per second. Your units should make sense. And the next one is going to be 113,097 centimeters squared per second. I didn't bother putting in the decimals because you can calculate this yourself, right? So what does this tell us here? What did they ask us for? We found these. That was no big deal. But now they say, what can you conclude? Well, look at the change in area. It changed after 2 seconds by about a factor of 3. But it changed by, how much is this? Like, let's call it 45K. How much did it change by here? It seems to have changed by about 45K. But is it actually? I'm going to let you calculate that and see. What is the change in area over time? And more importantly, energy is conserved in this kind of a system. So as the area increases and as the ripple moves outward, all of the energy that was in something this size is now in something this size, which means as it expands, it should be reduced, because look at how much space you have here in comparison to this space here. All this energy is spreading to a larger surface on the outside, or an area for the total. Why don't you subtract these from each other and see what you get? I think you'd be curious enough to find out on your own. But all you need to do here is find the derivative of area over time. That was really what they're asking for. And then plug in the time itself, and you end up with your answer.